All right. Last time we talked about arithmetic operations on sequences, and we just barely started that. But we proved the theorem that says if an converges to the real number a, and bn, the sequence, converges to the real number b, that implies that the new sequence converges to a plus b, where the new sequence is just what you get when you add the corresponding terms of the previous sequence. Some real simple examples we can look at would be, let's take an to be the sequence 2n over n plus 1. And let's take bn to be the sequence negative n over n plus 1. So obviously these go for all natural numbers n, from n going from 1 to infinity in both of those cases, n going 1 to infinity. Well, let's think about what we get when we combine the sum of these two. Let's first use the theorem. What does this sequence converge to? Do we remember?
2.
Yeah, we did one similar to this earlier. That converges to 2. And bn would converge to negative 1. So negative 1. So we expect this sequence when we add them together. Well, we don't expect it to. It is going to converge to 1. And let's convince ourselves by just doing the arithmetic on it. An plus bn for each n is 2n over n plus 1. Adding this would give us a minus n over n plus 1. And we can just do some simple arithmetic in there to simplify it to get denominators n plus 1, and we get n over n plus 1, which we know converges to 1. So as expected, that's one example showing that the theorem works, and it works in all cases. Now remember, a has to be a real number, and b has to be a real number as well. They can't be approaching infinity or negative infinity or divergent sequence of any form. Okay, well, the next one we're going to look at is similar statement, only we're not going to add the corresponding terms together, we're going to multiply them. So theorem 1.9 says the following. If an converges to the real number a and bn converges to the real number b, I'll be a little more precise here. I'll say as n approaches infinity.
Is that theorem 1.9?
Yeah. Oh yeah, sorry, thank you. It's 1.9. Threw an extra 1 in there. Thank you. So if an converges to the real number a, bn converges to the real number b, as n goes to infinity, then, and I'll let you tell me what to write here. If you multiply the terms together, it makes sense that it would converge to, yeah, capital A, capital B. I may have to write a little bit smaller on this one. The proof is similar to the previous theorem proof, but there's a little bit more algebra involved. All right, now something I'm going to write down temporarily is, let's just think ahead to what this proof has to look like. We're trying to prove that a sequence converges to its limit. So at some point, we're going to say, and I'm going to erase this in a minute, you don't have to write it down if you don't want to, we're going to have an epsilon bigger than 0. We have to find a capital N, and it might be a function of whatever this value is of epsilon. It may have epsilon as part of it. We have to find the n such that when n, little n, is bigger than the capital N, what's the big conclusion? What's just the last statement we write here? Last expression. We're proving that AN, BN converges to AB. So the distance between A and Bn and AB has to be small, and less than epsilon, right? So the absolute value of A and Bn minus AB is less than epsilon. That's the sketch of our proof. We haven't shown any details, though. So let's go ahead and start. That let epsilon greater than 0, that is the first line of the proof. Let epsilon greater than 0 be given. So epsilon is an arbitrary positive number. Now, what I'm going to do with the sequence AN, I'm going to say let capital M, it could be any positive real number, so I'm going to say let's let it be a natural number. Therefore, we know it's positive. Be such that, and I want capital M to be a bound. And I won't write down the justification for that. Why am I allowed to say that, though? Why do I know that this M exists? Let M be a positive number, a natural number, such that absolute value of every single element in this sequence is less than or equal to M. If I were going to put a little justification, I could say convergence implies bounded. Remember that? We wrote that as a lemma or a theorem recently. So if it's bounded, that means that it's bounded above. In this case, I'm bounding it above by positive M and bounding it below by negative M. So it's squeezed between those two numbers. All right, maybe this won't look nice, but I'm going to define an epsilon prime to be equal to epsilon over the absolute value of B plus M. So B is the limit of the sequence of the Bn's. Capital M is just a bound, a number, for the sequence AN's. AN. Obviously, epsilon prime is bigger than 0. You'll see why we picked this, when we get to the end of the proof. And yes, we could have figured this out if we just walked through the proof. If I just used epsilon instead of epsilon prime, we'll see at the end of the proof why, that wasn't quite good enough. I need to start off by defining this epsilon prime. All right, let's let capital N1 and capital N2 be natural numbers such that if n is greater than n1, that implies the distance between an and a is less than epsilon prime. Why are we allowed to do that? Why does that n1 exist? Well, simply because an converges to a. That's almost the definition of convergence. And I think I'm going to have to, I don't want to keep going down here, so I'm going to say, and n greater than n2 implies the same thing for, or corresponding thing for the sequence Bn. Now, I want to have a natural number n that makes both of these statements true, so I'm going to have a capital N that I'll define as the maximum of n1 and n2. And to save some room below, I'm going to put let n equal the max of n1 and n2. Therefore, if little n is bigger than capital N, well, then it's bigger than n1, which means this is true. And it's bigger than n2, which means that's true as well. All right, now we're going to dive into the final statement. Should I put thus or therefore? I'll put thus. AN, BN minus capital A, capital B. I'm going to do some arithmetic, but eventually I'm going to show that that's less than epsilon, and that'll be the end of the proof. Well, let's add and subtract the same number from this, which will be net result of adding 0. I'm going to say an bn minus anb, that's an capital B, plus an capital B minus ab. So obviously these are equal because all I did is add 0. Negative a and b and positive a and b. And maybe we'll put that in parentheses to make it look like two terms being added together. Well, notice in each one of those terms you can factor something out. So let's factor it out. This has an an in it. And that would be an times bn minus b plus, I'm doing two things in one step here. I'll ask you what it is when I'm done here. Factor out the b, an minus a. There's one thing I'm going to change on that line, and it's not going to be equal anymore. Since I did two things in, yeah, exactly right, Namdi, it's less than or equal. I had these as two separate lines in my notes, but I'm running out of room, so I did two things at once. So the absolute value of this plus this is less than or equal to the absolute value of the first one plus the absolute value of the second one by the triangle inequality. So I did a little bit of factoring, and I used the triangle inequality as well. Well, that's exactly equal to, here's what I'm going to use. I'm going to say that the property of absolute value says I can break the product of the absolute value of a product into the product of the absolute values. So let's take out an by itself and bn minus b by itself plus just like that. And you'll notice that these are looking familiar. We know upper bounds for both of these, right? Each one of these is less than epsilon prime. And I actually have an upper bound for an as well, right? The absolute value of an. Yeah, capital M. So that's less than, say it.
That's still less than equal to?
This is equal. Because all I did was this. And that's exactly equal in that case. So this is less than M. Well, bn minus b, remember n is greater than, let's see, did I say anywhere? Let n be the maximum of those two numbers. So technically I need to say thus for all n bigger than n. So let me squeeze that in here. N greater than capital N implies this. I'll make it look a little clearer. N greater than N. So if n is bigger than n, then I know an is less than m. I know that bn minus b is less than epsilon plus b epsilon prime. Actually, this is a strict less than, isn't it? Because I know this is less than epsilon prime. This is less than epsilon prime. Well, if we factor out the epsilon prime, we get that. What is that? Epsilon. Exactly right. That's why we chose this epsilon to be that ugly expression on the right here. So if you take this and multiply it by absolute value of b plus m, or switched around, it cancels out and we get epsilon. So we've shown that whenever n is bigger than capital N, we found the magic n we needed. Whenever that's true, an, bn minus ab is, as you follow these down, you stick with the less than. We get an, bn minus ab is less than epsilon. Maybe I'll put a comma there and say and an, bn converges to ab, and that'll be the end of the proof. Any questions about the theorem or the proof? Now, if you're afraid that in the homework you're going to have to come up with an expression like this, an epsilon prime, you'd be able to come up with it. If we didn't define epsilon prime, we would have ended up with, now don't make the changes I'm going to make here, we would have come up with this being less than epsilon times that, and I needed it to be epsilon. So I made the temporary epsilon where I divided this out of it, like that, to make it work in the end. So it wouldn't have been difficult to figure out what we needed to use for the epsilon prime. No questions? All right, well, let's take a look at some implications of theorem 1.9. Some examples maybe, and actually we'll learn a little bit more than just theorem 1.9. Let's suppose that AN converges to A. So we have a convergent sequence, it converges to the real number A. I'll use that for all the little examples we do to follow. Let's say that Bn, the sequence Bn is equal to -1, the constant sequence -1. Which I could just write out -1, -1, -1, ... Well, by the theorem 1.9, what do we know? Well, we know that the sequence Bn converges to -1 because it's the constant sequence -1. So -AN, so I'm changing all of the terms, I'm making the opposite of them, multiplying each one of them by -1, which that's also equal to AN/BN. For all n, this is true, correct? Because Bn is just -1. Well, we know that this converges to AB, which is capital A times -1, which is just, I'll just write -A. So that tells us when we just take all the sequence elements, multiply them by -1, instead of converging to A, it's going to converge to -A. That makes sense. That would be a very simple proof as well. But more generally than that, that's going to work for not just the constant -1 sequence. We could say that, let's see, let's consider this sequence. I'm going to call it just alpha, where alpha is a real number. So again, it's a constant sequence. It doesn't have to be -1, but it's a constant sequence. Since the sequence alpha converges to alpha, we know what the new sequence AN times alpha converges to by theorem 1.9. If I take alpha AN, it's going to converge to alpha times A. So a real specific example would be if you doubled all the values in the sequence AN, that new sequence is going to converge to A doubled, or 2A. All right, hopefully I can get this in. Even more generally, this I should write as a theorem. This is something you should memorize. It's the generalization of many of our arithmetic on sequence theorems. More generally, if an goes to a, converges to the real number a, and bn converges to the real number b, and alpha and beta are any two real numbers, then a new sequence obtained by taking what we would call a linear combination of the values in the sequences, it would be, this is a comma here, if we took alpha an plus beta bn, that's a new sequence obtained by, with the first sequence we multiplied all the terms by alpha, the second sequence we multiplied all the terms by beta, and then we added those together. What's that going to converge to? Yeah, alpha times a plus beta times b. This, I'm going to put a star by it. We can assume that we know that from now on. I should have given that a named or a numbered theorem. Textbook didn't. But from now on, we can just assume that we know this theorem. You can use that in proofs. All right, I have a question now. It's just a true-false question. If neither an nor the sequence bn converges, neither one of them converges, then an bn does not converge. True or false? If it's false, you have to give me a counterexample. If neither an nor bn converges, then when you multiply the corresponding terms, it's impossible for that sequence to converge as well. Did you say?
I think it's false, but I'm looking for a counterexample.
There's an infinite, they're really easy to come up with counterexamples. I'm just going to draw the picture of one. I'll draw these sequences like a function. The 1 over n. Let's take a over n, or sorry, an is 1 over n. So it starts with 1, then 1/2, then third, fourth, a fifth, and so on. And then bn, what could I take? Oh, sorry, let's see. That's convergent. This will be my example for the next theorem. How about, yeah, I came up with a counterexample to the wrong thing. But there's a real simple one anyways. Very obvious. The constant, nope, that's convergent too. All right. Think of one. I don't have an example. So what you're having to do is find two sequences that don't converge, but when you multiply them together, they do converge.
Would an alternating series like -1, 1 be one of the possibilities that does not converge?
That's exactly what I have written down. And I thought it was the wrong counterexample. Yeah, I was thinking, what I was thinking of by not converging, they were maybe unbounded going up to infinity, when I shouldn't have been thinking about that. Exactly right. Thank you for convincing me that my example was actually right. If you take, what was it? Were you going to do an alternating? Yeah. The an could be 1, -1, 1, -1, 1, -1, and so on. It doesn't converge. It's not approaching any number. Every number is either 0, is either -1 or 1. Bn, I'm going to do what? So let's see, I want to make sure I get this right. It's going to be -1 to the, I want the first one to be positive here, so I'll say n plus 1. And b is going to be bn will be the sequence almost the same, -1 to the n. So this one starts off 1, -1, 1, -1, dot, dot, dot. This one is -1, 1, -1, 1. Neither one of them converges. When you multiply them together, you get the constant sequence -1, right? So that's an, this would be bn. The green one is the bn's. And then multiply them together and you get an bn is equal to the constant sequence -1, because the corresponding terms 1 times -1 gives you the -1. Thank you for straightening me out, Allison. Okay, well, eventually we're going to prove that when you have two convergent sequences, an, bn, if you, under some circumstances, an over bn will converge. So we've shown that an plus bn converges, an times bn converges, and do you agree that we've already shown this? Do you agree we've really already done this? That if you subtract them? Because we showed that this is the same as plus a negative bn. And an we know converges to a, and negative bn we showed converges to b. So we've got the subtraction case taken care of already. Well, there's a lemma we'll need before we do the division case. And this lemma can be thought of, lemma 1.10, as bounding a sequence away from 0. Now you can only do that if the sequence converges to a number that's not 0. But if bn converges to the real number b, and I have to specify where b is not equal to 0, then there exists a natural number n such that if little n is greater than that capital N, all of the elements of the sequence are greater than or equal to a number that I didn't yet define. Okay, then there exists an n and an m. M has to be a positive number. So I'll say R plus. Can't be 0, it has to be a positive number. So before we do the proof, I'll draw a little picture of it, but let's make sure we understand what's being said here. Bn converges to B. Let's say that B is there. So the sequence eventually gets very, very close to that line B, to the horizontal line B. Well, what this says is at some point, now maybe I should have put some down below, some negative numbers down there. We're trying to bound all the elements away from B. At some point, and you can see where that point is, from there forward, there is an m, which I will call this number m, which means this would be negative m. You remember what this means? When the absolute value of a number is greater than or equal to m, it means that number is either bigger than or equal to m, or it's less than or equal to negative m. So from some point forward, all of the numbers will be outside of this strip. And the way I drew it, they're all above it. If the limit b happened to be a negative number, then they would all be below the negative m. Pretty simple proof also. All right, proof. I just have to show that this n and m exist. So let's let epsilon be precisely the halfway point between 0 and the limit, half of it. So the absolute value of b over 2. And let capital N be the natural number such that, let's use this definition here, n greater than capital N implies Bn minus B is less than that epsilon. And the justification for that is simply that Bn converges to B. So we know that capital N exists. Now this is unusual, but we are going to define m to be the same thing as epsilon is. I could write down let m equal epsilon, but I'm just going to rewrite absolute value of the limit b over 2. And we're almost done here. Therefore, n greater than capital N implies the following. And we have to prove this. We'll start off with Bn. I'm going to add and subtract capital B. Those are obviously equal. I'm going to break this up into essentially two things. This plus that. And I'm going to use a version of the triangle inequality, a little bit different than the version we all know. This is greater than or equal to b minus that. That's the version of the triangle inequality. The triangle inequality says normally that, I'll use